Okay, so it's my pleasure now to go with the very, very last speaker of this year, row series. So Simon Tomasz. So Simon is a PhD student in Aachen, so RWTH Aachen, but also has a PhD position at TU Munich, if I understood it correctly. Uh, So his research focused on robust optimization, adjustable robust optimization with applications to supply chain management and network design. And he's today going to talk about affine decision rules in many type of optimizations. So without further ado, I want to give the control of the mic and screen to you, Simon.
Yeah, thank you for the nice introduction, and thank you for inviting me to give a presentation in this webinar. I always enjoy following all the other talks, so hopefully you also enjoy following my talk today, which is a note on piecewise affine decision rules for robust, stochastic, and data-driven optimization. So the problems that we are studying in this talk are the following stochastic problems. And I know this is the robust optimization webinar, but you will hopefully see in a second why this is also interesting for the robust optimization community. So we study stochastic problems which aim to minimize the expected value over some linear objective function, which can be subject to some uncertain parameters, such that a set of G constraint sets with robust parameters are fulfilled. So we have capital G sets of robust constraints here, which all have to be fulfilled. And we do this in a multi-stage setting, so we want our decisions to be non-anticipative. So maybe just a brief recap, probably most of you are familiar with this. In a multi-stage decision setting, we have to make some decisions X, observe some uncertainties, and then alternatingly make some decisions again and observe some uncertainties. And non-anticipativity means that in each stage T, we are only allowed to make our decisions depend on uncertainties that were observed before. So we are not allowed to cheat and look into the future. And for the rest of the talk, we hide most of this dynamic in the set F here and just write psi for the uncertainty and X for the decisions. And whenever the uncertainty is from some probability distribution, we indicate this with the tilde here. So why study this slightly strange problem? It turns out many classical problems are special cases of this. So first we have stochastic programming with almost certain constraints, which we can achieve by just taking a single set of constraints and have the uncertainty set as the support of the probability distribution. Then we have classical robust optimization, where we can augment the problem with an epigraph formulation and then move this robust term from the objective to the constraints, and we end up with a deterministic objective function where we can choose any arbitrary probability distribution and solve this. And finally, and this is why we go through the hustle of having these G sets of constraints, we can do data-driven optimization with type infinity Wasserstein balls around some empirical distributions. And the reformulation for this goes back to a recent paper by Piecewise et al. And for the rest of the talk, you can essentially take the problem which you like most and just think this problem, because it doesn't really matter too much which of these problems we want to do. So throughout, in general, this problem is hard. So this is an NP-hard problem, which is commonly known because all the special cases that I just mentioned are NP-hard. And one approach to solve this is to restrict the decisions to tractable decision rules. And there's a whole bunch of different approaches to do this. And I'm not going to go through all of them. And this is probably not even a comprehensive list. maybe as one example, the most prominent choice probably are affine decision rules. And affine decision rules work in a way that we restrict the decisions at any stage t to be affine in the uncertainties that were observed before. So we have some affine scaling matrix P here and some constant PT, and then the decision that we take is just this parameters capital and small p. And in this talk we study and extend piecewise affine decision rules that use a concept called lifting that were introduced by Gorgio et al. In 2015 in the context of stochastic optimization. So the talk is structured as follows. So first we prove that the way the decision rules were originally introduced, they yield no improvements over affine policies in a robust setting. And this is a phenomenon which was actually observed numerically, but somehow no one has looked at it from a theoretical perspective yet. Then we show how to improve these decision rules and overcome this shortcoming, such that we can also use these decision rules in a robust setting, and also we want to be able to use them in this data-driven setting. And finally, I'm going to show some numerical experiments that that show that whatever we do here also works in practice. So how do these lifting rules work? So if we consider affine policies, these are relatively limited. So we are just affine in the uncertainty realizations and get some affine decisions here. And the idea of the lifting is, let's create some new features in some higher dimensional set and then use affine policies on this here. And maybe as an intuition, most of you are probably familiar with linear regressions. When we do linear regressions, we are always linear in the features that we feed to the linear regression. However, by doing some smart feature engineering, we are not necessarily bound to linear functions in the original features, because we can just introduce nonlinear features and then we get a nonlinear function in the original features. And this is exactly the idea of the lifting. But we don't want to use any arbitrary lifting, because then things might get pretty complicated. So we consider a special kind of lifting, which consists of two parts. The first part of the lifting is some linear embedding, which we can use to add features, so new feature directions, and to make the uncertainty set look nice in a way. And nice could be something like going from an ellipsis to a nice symmetric sphere. And this linear embedding has a left inverse, which allows us to go back in a nice affine way. And then the second part, this is where the interesting stuff happens, is for each of the dimensions in the embedded space, we choose breakpoints. And then along each of the intervals between breakpoints, we have a piecewise affine function that lifts our uncertainty into new uncertainty dimensions. So for each of the dimensions in the embedded space here, we get the number of breakpoints, new dimensions in the lifted space, where these are coupled by these piecewise affine functions. And then we can go back here by just summing up all the features, which is a nice affine function. So again, here we have a left inverse, which is nice and affine, but the lifting part is piecewise affine and non-convex action. So how does this look? If we now take one dimension in the embedded space with a single breakpoint, then when we lift this becomes two-dimensional and is of this L shape here. And as you can see right away, this is non-convex, and this is also not tractable to solve. So the idea is, let's get some outer approximation of this lifted set here and work with this outer approximation, which is hopefully tractable. And the way it was originally proposed, this outer approximation consists of two parts. And both parts essentially relax the condition that our lifted realization has to be part of the lifted uncertainty set. And the first part uses the left inverse of the folding operator here, which if from the last slide we know is just an affine function. So this is a nice function. And then we have an affine function here, and then we have the embedded set here, which whenever the original uncertainties that we started with is nice, is also nice, because this is just an linear transformation of the original uncertainty set. So this is a nice and tractable condition here. And then for the second part, we take the bounding box of our embedded uncertainty set, then we fold this, and we take the convex closure of this. And for sure, everything which was an element in the original lifted set is also in this convex closure of the bounding box. And this also has a nice linear formulation, which I'm not going to show here, but this is also very tractable. So why do we go through all this hassle? So if we take the original problem and the lifted problem, then if we allow ourselves to take general decision rules on both of these problems, then these are exactly equivalent, because we could just augment any decision rules by the lifting and then get a decision rule in the other problem. So for this doesn't help us yet. But if we restrict ourselves to affine policies, then affine policies in the lifted setting, they are more flexible than in the original setting. So any approximation for the fully adaptable problem is tighter in this lifted setting than in the original setting. However, if we take the general lifted set, this is untractable. But the nice thing is, and this is why the approach works, if we take the outer approximation, we still have this property. And this is essentially what the original paper did. So they have this outer approximation and they use the affine decision rules there, and they get better performances than the affine decision rules in the original setting in the stochastic case, because the original paper purely focused on the stochastic case. And while some of the constructions that I just showed you to our more generalized problem are not directly straightforward, going from the stochastic setting to the robust setting to the classical robust setting is super straightforward. This is super easy. And people have done this, but whenever they did this, they found that the policies in the lifted setting with this outer approximation yield exactly the same results as the affine policies, which is a little unfortunate, because you went through all this trouble, constructed this new lifting, constructed this outer approximation, did all the breakpoints, you spent a bunch of extra computational time on computing your solutions, because this is a more complex problem to solve, and in the end you get exactly the same results. And we can actually now formalize this. So essentially what we can show is all improvements of the affine approximation with the outer approximation in the lifted setting here over the affine approximations in the original setting originate from a tighter approximation of the stochastic objective function. And I want to give you a very high level idea of the proof here. So for this, let's state a slightly more formal result. So if we are in the setting where we only have one set of robust constraints, then there exists some subset of the outer approximation which retracts to original set. So if we go back down with the nice affine functions, we end up getting the full original uncertainty set, such that every feasible solution in the lifted setting has a corresponding feasible solution in the original setting that correspond on this subset here. And essentially what this means is that whenever this here is feasible, the X in the lower setting is also feasible. And the proof of this resembles around relaxing this this folding function here, this non-convex piecewise affine functions. And the idea is, well, let's replace this non-convex part with a nice affine folding, where we just map every uncertainty dimension in the embedded setting equally to all the lifted dimensions. And this is an affine function. And this would be something like the blue line in this two-dimensional example here. So instead of mapping to this green L-shaped thing, we map to this blue one. And the nice thing of this this affine thing is, if we again sum up along one of these dimensions, we end up getting the original embedded uncertainty. So we can use this property that we have the left inverse again, and construct a new affine function in the original setting by just concatenating this now affine lifting with any solution to the lifted setting, and end up getting a feasible solution on the original setting. And a direct corollary of this is that in the robust setting, where we don't have this stochastic objective function anymore, the affine approximations on the lifted setting with the outer approximation are exactly the same as the affine approximations on the original set. And for the rest of this talk, I want to briefly show you how to overcome this shortcoming. Okay, so the idea of tightening the outer approximation resembles around breakpoint rectangles. So what are breakpoint rectangles? So if we take all the breakpoints, they span a grid in the embedded space. And if we now take two of these breakpoints, of these grid points in this breakpoint grid, they span a hyperrectangle. So in 2 dimensions, it's just a rectangle, but this is a hyperrectangle. And we can now measure the one norm distance from this rectangle for any uncertainty realizations in the embedded space. So this is just a distance. Then this is clearly upper bounded by the maximum distance any point in the embedded space can have from the rectangle here. And now the interesting part is we actually have a nice affine upper bound for all the points in the outer approximation of the lifted setting. If we take them back down to the embedded space, so go back to this embedded setting here, then we can upper bound the distance to the rectangle by this affine term, which is affine in all the components that belong to intervals that are outside of the rectangle. So this is the components that are essentially to the left and to the upper part of this rectangle. And this is the components which are here to the lower part. And this inequality here is tight for all the realizations in the actual lifted set. But this is not necessarily tight for all the other realizations in the outer approximation. But because it's tight for all the realizations in the actual lifted set, we get valid inequalities here, where we can bound this affine term here by the maximal distance here. And this is essentially the inequalities that we are going to use to tighten the approximation. So how do we solve this problem now? So this is the dual of the lifted problem with the outer approximation. It doesn't matter too much how it looks. So essentially the first two constraints here are the dual constraints for the decision variables of the affine decisions here. And this is pretty standard. And then the last constraint is a scaled version of the outer approximation. And now if we add our additional constraints, then these become new constraints in the dual formulation. And these are actually linear constraints. The only thing which is not so nice about them is these are exponentially many, because there's exponentially many of these breakpoint rectangles. So what we can do is we solve this via constraint generation. Only drawback, in general, the separation problem, unfortunately, is NP hard. So this is not so nice. The good thing is, under relatively mild symmetry assumptions, the separation problem gets easy. So we can solve it in polynomial time. And many prominent uncertainty sets fulfill. So budgeted uncertainty, hypersphere uncertainty, arbitrary normal intersection, they all fall in this mild symmetry assumptions. And then with the embedding operator that we had before, we can also do things like ellipsis uncertainties. And then furthermore, if we have some additional technical assumptions, which I'm not going to show here, we can actually show that O of I, where I here is the dimension of the embedded set, cuts are sufficient. So we don't have to do any constraint generation at all. We can just add these cuts right away and then we're done. The only thing we lose here is essentially norms with norm equal to 1 or equal to infinity. But this still holds for relatively general cases. Only thing is we have to add relatively many breakpoints to achieve this. But this is a design decision, adding the breakpoints. So let's briefly go into some numerical results. So in the numerical results, we're going to compare the following policies. So first we compare classical affine policies. Then we take our lifted affine policies with our tightening constraints and without the tightening constraints here. So this would be the original setting. With a single breakpoint. Then we do this with 3 evenly spaced breakpoints. And then the last thing is this full breakpoint setting. So essentially here we add sufficiently many breakpoints that we can use this O of I cuts, so that we don't have to do constraint generation. And we test this on a single product multi-period inventory replenishment problem, which I'm not going to show here because I think the problem formulation is not too interesting. And we jump directly to the results. And here the alpha is an autocorrelation factor for the uncertainty between stages. We test on different numbers of stages here, and then we scale all the results by the performance of the affine policies. So affine policies are always scaled to 1. And then what we can see is lifting policies perform up to 60% better than affine policies in the stochastic setting. And adding our additional cuts gives us up to 10% performance improvements. And this is kind of what we expected because the original lifted policies already outperformed affine policies in the original paper. So this is a nice sanity check here. And we can do this for relatively mild improvements in runtime. So as long as we only add a few breakpoints, then the runtime doesn't explode. But as soon as we add many breakpoints here to get this full setting, then actually adding our additional cuts lets the runtime explode. So it's probably a good idea to choose the breakpoints wisely. Then in the robust setting, we showed that if we don't do our additional tightening of the outer approximation, then we don't get any improvements over affine. So essentially, this is also in the line up here. And with the additional tightening of the outer approximation, we get improvements up to 40% over the affine policies. And the runtime behavior is pretty similar as in the stochastic setting. And now finally, when we go to a data-driven setting, we now vary the number of samples that we choose, where we then take the empirical distribution of the samples and take Wasserstein balls around it. And the epsilon here is the size of the Wasserstein balls. And what we can see is when we vary the size of the Wasserstein ball, then we can see improvements of up to 20% over affine policies. However, if we take small sample sizes and small radii, then we have significant overfitting. So what we tested also was doing cross-validation, and when we do cross-validation, we always outperform affine policy. So that's it. So what we saw today is we saw that the classical approach of doing piecewise affine policies with this lifting setting doesn't give us any improvements over affine policies in the robust setting. We then showed how to improve the policies by adding additional cuts, and showed that in a numerical setting this works quite well. And there's a preprint available on arXiv if you are interested in the details. Thank you.